This unit is difficult for most students because everything is energy and heat. If you understand the small differences between each definition, this unit will be a lot easier. You already know that energy is the ability to do work, and that heat is a transfer of energy. Thermal energy is the total energy due to motion of atoms or molecule. So it is related to the kinetic energy, which is equal to 1/2 mass times velocity squared. So if we have a classroom and the temperature in the classroom is 100 degrees Celsius, but outside the temperature is 0 degrees Celsius, the thermal energy is much greater outside than inside because there are more molecules or atoms outside. So if I add up all the kinetic energy or the energy of motion of all the atoms outside, even though the temperature is lower, the thermal energy or the total thermal energy will be greater than the room, even though the temperature is higher because it has less atoms and molecules in the room. Internal energy, which is delta E usually in chemistry, but in physics is usually delta U, is the total energy, including the kinetic and the potential energy. So all the energy that exists for atoms and molecules, they are all added, whether they are moving or not. And temperature, we said, is proportional to the average kinetic energy. As the temperature increases, the average kinetic energy increases because they're directly proportional. Enthalpy is H. It is also known as the heat of reaction. It is the total or the change in heat at a constant pressure. It measures heat flow. So it only depends on the initial and final state. This is why it is a state function. Because it only depends on the initial and final state, the path it takes to reach the final state does not matter. So it is very difficult to measure enthalpy for one particular thing. It is usually the change that is measured. Q, which is heat, is equal to delta H, which is the change in enthalpy or change in heat of reaction or enthalpy of reaction, are interchangeable when it's at constant pressure. This is why in class a lot of times we say Q is also equal to delta H. Molar enthalpy is energy changes or delta H or change in enthalpy or change in heat of reaction involved in 1 mole of substance. Since it's 1 mole of substance, the units will be joules per mole or kilojoules per mole. The first way you will see enthalpy written is delta H solution. This is the heat change caused by dissolution or dissolving one substance into another substance to create a solution. A lot of times it is a solid being added to a water. When a solid is added to a water, sometimes we will see delta H solution as Q solution, in which Q solution is going to be MC delta T, in which mass here is going to be the total mass. So if it's two individual solution being mixed, then it will be the total mass of solution added together. That means that volume is additive. If it's a solid being added to water, then the total mass will be the mass of the solid plus the water. Unless given, to find the mass, you're going to use the density of the water. If volume is given, you're going to use C for water for the constant. The second way you will see enthalpy of reaction is in a combustion reaction. So it's going to be abbreviated delta H COMB for combustion. It is the heat released when 1 mole of substance is completely burn. So it is any type of combustion reaction, like we discussed in class. We have methane here. It reacts with O2 to produce CO2 and H2O. It could be an alcohol, which is CxHyOZ plus O2 will produce CO2 and H2O. But it could also be the combustion of producing water. It could also be a bomb calorimeter. You burn the food is being combusted, and all the heat goes into the water and the bomb calorimeter. Here too, you want to use units of joules per mole or kilojoules per mole, because delta H is for 1 mole of substance. The third way enthalpy will be written is in a neutralization reaction. Delta H, neut. This is heat change in an acid-base reaction. An acid-base reaction will produce a salt and a water. A salt is an ionic compound in which the cation is from the base and the anion is from the acid. When I have a neutralization reaction, the volumes will always be additive unless they tell you it's negligible. Unless given, we use the density of water to solve for the mass of the solution and the C of water for the heat constant. A lot of times you will also see this as delta H. Neutralization is also equal to Q of solution. The final way you will see enthalpy is the standard enthalpy of formation. This is from its elements. It is labeled delta H subscript F. If it's in standard state, you will see this degree sign. This is the enthalpy change when 1 mole of compound is formed from its elements in standard condition. Standard conditions are 1 mole. 1 atm for temperature is 25 degrees Celsius. If it's a pure solution, it's 1 molar. At standard states for the elements, this is off the periodic table, delta HF naught is equal to 0 kilojoules per mole. So for example, if you have H2, it is a gas off the periodic table. This is its standard state. Delta HF naught is equal to 0 kilojoules per mole. However, if we have H2 liquid, this will have a value. When the standard heat of formation is negative, it tells you that element is very stable. When the value is negative, it tells you the element, compound, whatever is very stable. If it's positive, it is very unstable. To estimate the heat of reaction for the standard formation of enthalpy, the general reaction is products minus reactant, in which the sigma sign is the summation of all the products multiplied by its moles. These values you get from your appendix at the back of your book. So these are given, or you will be solving for it, of the products minus the summation of all the reactants. So if I have a general equation in which the coefficients are the small letters and the elements or compounds are the capital letters, the general equation that we have will be the moles of C times the delta HF naught of C, the moles of D times the delta HF naught of D, and these will be added. So we're adding all the products, and if there is more products, we add them all, minus my reactants, which A and B are my reactants. So we find the moles of A, delta HF naught of A, minus moles of B, delta HF naught of B. Where do we find the moles? We must write a correct balance equation. So the moles are going to be the coefficient, as usual, of the balance equation. And please note that if it's at its elemental state, the delta HF naught is going to be 0 kilojoules per mole. Hess's law is also delta H reaction. It is also enthalpy. It is the overall enthalpy change in a reaction. Hess's law states that the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for all the individual steps in the process. So what that means is if a reaction occurs, it could proceed in one step or multiple steps. Whether it goes through one step or multiple steps, the delta H of the reaction will be the same. This is why enthalpy is a state function. It only depends on the initial and final. So a couple rules we need to do is number one, if we reverse the reaction, the sign of the delta H must change. So if it was a positive delta H reaction in the forward direction, in the reverse direction, it must be negative. If I multiply or divide the reaction, I must multiply or divide the delta H, because remember, it is per mole. So for example, here we have the combustion of methane. When methane is combusted in one step, it has a delta H reaction of negative 890 kilojoules. However, the combustion of methane can also occur in two steps. The CH4 plus O2 can go to CO, carbon monoxide, plus water, plus half an oxygen. And then it could do step 2 when it converts that intermediate step to CO2 to H2O. If I add up my first step, delta H1, which is negative 607, with my second step, delta H, which is negative 283, we still get negative 890 kilojoules. So enthalpy is a state function. We don't care how many steps it takes to get there. The end result, or the change in enthalpy of the reaction, will be the same.